Welcome to The Foundry by Forge College. Today we're unrolling the engineering blueprint to take you from simple reliability to massive, massive application scaling. In our last explainer, we covered the reliability and uptime benefits of Cloudbreak, really zeroing in on blast radius isolation. But today we're taking the title of our explainer, scaling applications with Cloudbreak advantages, and putting it into concrete practice.
So we survived the crash. Phew, right? That was the whole point of our last session. But here is the multi-million-dollar question. Can we handle the crowd? Look, we've all experienced that classic developer panic. You know, that sudden cold sweat, that desperate prayer to the server gods when 10,000 users click buy at the exact same millisecond. Well, it turns out that the blast radius isolation we built last time, it's actually your secret weapon for handling massive read traffic. It's not just about surviving failure anymore. We are weaponizing that architecture for pure speed. Okay, let's dive into this explainer's agenda. We're looking at the precise roadmap for upgrading your systems. First, from reliability to scaling. Second, mastering the parallel read. Third, order books and indices. Fourth, the integration decision workflow. And finally, operationalizing your gains. All right, part one, from reliability to scaling, translating architecture into throughput.
Let's start by looking at how isolating failures at the state partition level naturally creates distinct, high-speed lanes for your data flow. I mean, think of legacy state management like a single, super congested warehouse aisle. Everyone is trying to get their goods, bumping into each other, just waiting in line forever. It's serial, and frankly, it's painfully slow. Cloudbreak, on the other hand, is like organizing that massive warehouse into parallel aisles. Suddenly, you have multiple robotic forklifts, which in this case represent our RPC requests, operating simultaneously in their own dedicated lanes without crashing into one another. It's a total game changer.
Moving on to section 2, mastering the parallel read, the code behind the speed.
So let's look at the actual technical schematics. How do we command those parallel forklifts right inside our code? Well, to fetch this data concurrently, we use a JavaScript method you're probably very familiar with, promise.all. In a Cloudbreak-optimized environment, we use promise.all to concurrently fetch multiple disjoint state partitions. This completely, absolutely removes that bottleneck of waiting in line. We aren't doing serial fetches anymore, guys. We're launching our requests in parallel across all those separate warehouse aisles.
But wait, we can optimize this even further. You pair that concurrency with the getMultipleAccountsInfo tool. And what this does is batch your reads within a single physical partition. So, going back to our warehouse analogy, instead of sending a forklift down an aisle just to grab one single box and drive all the way back, you're effectively filling up that entire forklift with a batch of boxes before sending it down its dedicated aisle. This drastically reduces your RPC overhead.
Section 3. Order books and indices. Prototypes in action.
Now, it's one thing to talk theory, but practical application is where the magic actually happens. Let's look at 2 concrete, state-intensive application prototypes that perfectly demonstrate these advantages. First up, the real-time order book, partitioned by market ID. Market makers require blazing fast speed, right? Well, by placing each market state into contiguous storage partitions, they're hitting sub-10 millisecond latency. Why? Because reads for different markets literally just do not compete with each other. On the flip side, we have the content serving index. High-traffic content apps group their top 5% of hot index entries together. This creates massive cache-friendly reads that are just incredibly efficient for metadata and search. And what's really fascinating here is the raw data. I mean, the metrics are staggering. Your average read latency drops from between 12 and 20 milliseconds, all the way down to just 5 to 9 milliseconds with Cloudbreak partitioning. Your RPC calls per second for the exact same traffic drops from 6,000 down to 3,200. Plus, your cache hit rate nearly doubles, jumping from 40% to 75%. Now, why does all this matter to you? Because dropping latency by over half and doubling your cache hits maps directly to cheaper read-serving infrastructure and absolutely zero missed arbitrage opportunities. It is literal money in the bank. Which brings us to section 4, the integration decision workflow, deciding what to build first. Look, you might be incredibly excited to rewrite your entire codebase right this second. But let's be real, you can't upgrade everything at once. We need a strict integration decision workflow to prioritize our engineering time. This sequentially outlines the exact pipeline you should use. Step 1, quantify your read intensity and skew so you can find your heavy hitters. Step 2, assess partitionability. Ask yourself, can you map the state to disjoint key ranges? Step 3,
estimate your expected performance gain. And step 4, evaluate the operational cost and migration effort. You use this exact pipeline to find subsystems with natural partition boundaries that are currently suffering from read-heavy bottlenecks. And to find your perfect target, you use this sweet spot matrix. You are looking for the absolute highest payoff per engineering day. You want to target the high QPS, highly partitionable modules that require the lowest migration effort for your first early wins. Basically, if you have a module with greater than 10,000 queries per second and natural key boundaries, boom, that is your prime target for an upgrade. All right, our last stop, Section 5, operationalizing your gains, the final polish. So raw architectural speed is great on a whiteboard, but to actually survive and thrive in production, you must implement specific operational patterns. It's like eating your vegetables. You need connection pooling per shard to keep your caches hot and reduce warm-up latency. You absolutely must implement shardware caching so your eviction aligns with your access patterns. And critically, you need strict monitoring and service-level objectives, or SLOs, per shard to quickly spot any regressions in read latencies. Finally, always use a controlled rollout strategy. Validate your performance on a small subset of keys before you ever execute a full cutover. So, before you open up your IDE and start coding, I have a question for you. What is your first pilot subsystem going to be? Pick just one pilot, maybe it's a single market pair or one specific content category, and measure its current queries per second to set a solid baseline. Don't try to boil the ocean here. Start with a focused, measurable target to validate your gains. It is time to turn these architectural benefits into engineering reality. You've got the blueprint now. To dig deeper into these Web3 engineering topics, fully master this implementation, and explore our other educational resources, make sure to visit forge.college. So as you look at your architecture today, ask yourself, which congested warehouse aisle are you going to organize first? Thanks for joining me on this explainer by Forge College, and keep building.